Chapter 19 for Chemistry 2 is the last chapter that we're going to be doing this year, and it's all about organic chemistry. So we're going to be naming and writing different compounds such as alkanes, alkenes, alkynes, aromatic hydrocarbons, and pointing out functional groups in the structures and looking at polymers and a whole lot more. So organic chemistry is pretty vast, and we're just going to scratch the surface. So, in introduction, you learned in Chem 1 that organic chemistry is the study of carbon-containing compounds and their properties. Some industries that have thrived on advances from organic chemistry include polymers like plastics, artificial flavorings in food, especially like down in the bottom right, the picture of the Pop-Tart. If you have a Pop-Tart that's strawberry, it's not actual strawberries in the Pop-Tart. It is a compound that's made to taste like strawberries and smell like strawberries. Component extractions would be like if you have a coffee bean, you can extract the caffeine molecule from the coffee bean, and so then that's how we get decaf coffee. Energy fuels such as E85 and the like have all been developed using organic chemistry advances. So the backbone of organic studies has to do two elements, carbon and silicon. Carbon is greatly attracted to oxygen to produce silica and silicates that form rocks, sand, soils, glass, and this is very important in the geological world, the study of rocks and everything like that. So up at the top right would be a compound with silicon in it, but we're going to study more the carbon side of things because carbon has the ability to bond with itself or with other things, and it makes very long chains or rings, and it's just what we're going to do. One type of carbon compound is a biomolecule, which bio stands for life, so like biology is the study of life. A biomolecule means that it's a molecule that can produce, reproduce, or maintain life. So a little history about organic. We call carbon-containing compounds organic compounds. Originally, the distinction between inorganic and organic was based on whether they were produced by living organisms or living systems. Inorganic would mean without carbon, organic with carbon. And they thought that this was only the way to have it, where if the compound was not made by a living system, then it's not organic. It would be inorganic. But this was corrected when a German chemist called Friedrich Ware, up here in the right corner, was able to synthesize the compound called urea, which is on the stamp up at the top, and he was able to make it from an inorganic salt. And so by making it from the inorganic salt, he was able to show them that you can make organic molecules out of inorganic things. And so their thoughts and ways of thinking about organic chemistry changed because of him. So the simplest organic compound is the hydrocarbon. We've heard about it before. It has hydrogens and carbons in it. And this is because a carbon atom can form a maximum of 4 bonds with other atoms, either carbon or something else. And so, like for example, pure carbon would be diamond. And remember, the different shapes of diamond cuts is because of the arrangement of the carbon molecules, or the carbon atoms in the molecule. So, the simplest compound of carbon is methane. So whenever we have a picture up here of a compound, the black stands for carbon and the white stands for hydrogen. Okay, so methane has 1 carbon and 4 hydrogens. This is showing when carbon can bond to 4 things, but carbon can bond with less than 4 things using multiple bonds. So like down in the bottom left is carbon dioxide, in the middle is what's called ethene, and on the right side it's called ethine. And so they all have double or triple bonds. So we have 2 words, saturated and unsaturated. A saturated compound is one that has all single bonds between the carbons and anything else. So that means that every single carbon is bonded to 4 atoms. If it's unsaturated, that means it has multiple bonds, so like a double or a triple bond. And then the Because of that, the carbons are bonding to less than 4. So they're not their maximum amount. So down here in the bottom corner, this compound, the 2 carbons on the left side are unsaturated because of the double bond there. Because they connect to 1, 2, and 3 each. But the 2 carbons on the right side are saturated because each carbon is bonded to 4 different things. There's 4 single bonds coming off of the carbon. So that's why it would be called saturated. So we're going to see different ways to see all of these compounds that we're going to be dealing with. The most common ones that we will use when writing are either the Lewis structure, which we have already done before, or the extended formula. And this, we'll talk about how to write these in a second. On the left side is the ball and stick model. What the ball and stick model shows is that you have your atoms, but then there's space between each atom so that you can see where the bond actually connects them. And the space filling model does not show you that empty space where the bonds are connected. They just show if we had all of these atoms with their electron clouds, this is kind of the shape it would take. So the most simplest of all hydrocarbons are called alkanes, and this is because each carbon is bonded to 4 other atoms. There are no multiple bonds, only single bonds. So starting from left to right, we have methane with 1 carbon, ethane with 2 carbons, propane with 3, and butane with 4. Whenever we have these kind of alkanes, where all of the carbons are in a long straight chain, we call them unbranched hydrocarbons. So as you can see on the previous slide, the chains kind of zigzag, and that's because the carbon-carbon-carbon, or any bond angle when you have 4 things around the carbon, is 109.5 degrees. And this is because of everything wants to be as far away as possible to make sure those electrons are as far away as possible. And so the zigzag shape we will actually see when we build some shapes on Friday. Another couple things, whenever you have an N carbon for a hydrocarbon, they usually have 3 atoms connected to them, and hydrogens in the middle have 2 hydrogens connected. And this is because on the end, the carbon only has to bond with 1 other carbon, and so it has 3 open spots left, and so the hydrogens take those places. But inside the middle, the carbon needs to bond to 2 carbons, so that means only 2 spots are available, and therefore we have 2 hydrogens. So, condensing down the Lewis structure, because Lewis structures do take a while, so we're not going to be writing those all the time. We're going to be writing what's called a written formula and condensed formula. So go ahead and copy down the Lewis structure for an alkane with 4 carbon atoms. And notice all the hydrogens are all there too. So to write the written formula, what we do is we take the first carbon and put the carbon first, and then write how many H's are connected to it. Then we move on to the second carbon and write how many H's are there. Third carbon, how many H's, and fourth carbon, how many H's. And sometimes written formulas can get pretty long, and so in order to shorten it a little bit, we have what's called the condensed formula, where on the condensed formula we have the 2 outsides normal, so the CH3 is on both outsides, but inside the middle we put CH2 and put the CH2 in parentheses and number it with how many times it repeats itself. And so in this case it repeated twice, so therefore there's a 2 outside of the parentheses. So example 1, write the written and condensed formula for an alkane containing 6 carbon atoms and hydrogen atoms. Well, first, we don't know how many hydrogens there are, so let's go ahead and draw the Lewis structure of it. So first I would say draw 6 carbons in a row. Then each carbon needs a total of 4 bonds, 4 bonded things to it. So the outsides are each going to have 3 spots, And the insides are each going to have 2 spots. So go ahead and fill in all of your hydrogens. When you're finished, you should have 6 carbons in the middle and then 14 hydrogens on the outside. So to write the written formula, you just start on one end and write the carbon first. So if we're starting right here, that means we have CH3, and then just keep going down. Next we have 1, 2, 3, 4 carbons with CH2. And then at the very end, we have another carbon with 3 hydrogens. So this written formula can kind of go on. And now we can condense it. So still write your 2 CH3s on either side. And like we said before, we have 1, 2, 3, 4 CH2 being repeated. So we're going to put CH2 on the inside, and then a subscript 4 to tell us that it's repeated 4 times. And that's the condensed formula. So it's not too bad how to do this. So there's a general formula for all hydrocarbons, especially with alkanes. So if you ever know how many carbons you have, you can actually figure out how many hydrogens you're supposed to have. So the formula is Cn, so the number of carbons, N. To find the number of H's, you take 2 times N plus 2. So we just had 6 carbons. So if we had C6, that means to find the number of H's, we take 2 times 6 plus 2, which would be 14. And that's what we had. So in case you want to know, and so you don't mess up, you can go ahead and use that formula. So to name the simple hydrocarbons, if it's an alkane, which is what we're dealing with today, the structure has a prefix in front of the ending ane. So with 1 carbon it's methane, 2 carbons ethane, 3 carbons propane, 4 carbons butane, 5 pentane, 6 hexane, 7 heptane, 8 octane, 9 nonane, and 10 decane. The first 8 I would have kind of memorized, which 5, 6, 7, 8 have the prefix that you would use in geometry class. Like a pentagon has 5 sides, so that means it's pentane. And hexagon has 6 sides. Octagon has 8 sides. So those prefixes all kind of work. The first 4 are a little hard to memorize because they're just different. And 9 and 10, I won't give you one of those on a quiz or a test, just because they're not the most commonly used ones. But, and I won't make you draw a 9 or 10 chain carbon structure, so there you go. So example 2, and then we're done for the day. Name the following normal hydrocarbons. So basically you just count the number of carbons. So the first one has 1 carbon, so looking at the table, that's going to be methane. The next one down, we have 1, 2, 3, 4, 5 carbons. So that means it has the number for 5. Pentane. And then last is a condensed formula. So this one's kind of tricky, but we have 2 on the outsides and then 6 repeating in the middle. So that's a total of 8. So that name will be octane. Okay, so we're starting it pretty easy with organic chemistry. This is all I gotta do today, so I'll talk at you later.